Hello everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective. This is lecture number 23 and the topic of the lecture is SPICE models, and we will be taking some examples for it. So, in our previous lectures we have actually together went through the various levels of SPICE model and what physical parameters of the devices are enumerated in all those SPICE models that we looked into. So, in this lecture we will take each level and show you how to write a netlist and then generate the IV characteristics, current versus voltage characteristics for maybe an NFET we will do. We will not take PFET here and we will take NMOSFET and we will try to show you how it works out. So, with this let me start formally today's lecture. So, this is the outline for that we will be looking into the MOS characteristics. Here we will be looking into NMOS and PMOS. So, this will be more of NMOS and PMOS, right, and we will be looking into NMOS only, but NMOS we will do both level 1, level 2 and level 3. All these 3 levels will be looked into NMOS and then we will look into its IV characteristics of NMOS. So, current versus voltage as well as we will look into the transfer characteristics of NMOS. What does transfer basically means? Current versus applied gate voltage, and we will be also looking current versus drain voltage. So, two things we will be looking into. We will be looking into current with respect to drain voltage, and we will be also looking into current versus gate voltage. This one is referred to as the output characteristics, right, and this one is referred to as transfer characteristics. We will be looking both into them in detailed manner. Since we learned NMOS and PMOS, then I will give you a brief about CMOS inverter and give you a practical example in the SPICE model file. Once we know an inverter, or next logical way to move forward is to basically design a ring oscillator, right, using CMOS inverters. So, we will use that and show it to you, and then we will look into some analog applications and then finally recapitulate the lecture series here. This is your, so this is the first example which I am quoting in front of you, PSpice netlist. This is known as a netlist and this is basically level 1. If you look very carefully, this is level 1, right. And what we are saying is that you apply a VGS here, which is in at position number 1, and it varies from 0 to 2 volts, and VDS is again at 0 to 2 volts, but VBS is 0 volts. So, there is no body effect coming into picture. And then when we put a star in the front of a statement, it basically means it is a comment statement and it is just meant to showcase the readability or improve the readability of the netlist file. Subsequently, you see that the transistor M1 has been kept between all these nodes, and the channel length of the device is 3 micron and the width is 3 micron. So, the channel length L is 3 micrometer and width is basically 3 micrometer, right, micrometer. And therefore, if you look at W by L, generally we write down as 3 by 3. So, for the current transistor which we are taking into consideration, the width to length ratio is 3 by 3, right. So, L1, if you look here, L1 is basically the level of the SPICE file which we are taking into consideration, and then these are the nodes across which the transistor is actually kept, right. And the NFET, this is basically the sort of an initiation of the device, right, of the transistor. This part is basically the device parameters. So, what are the device parameters here? So, model file which I am taking L1 means level 1, and as you can see, therefore, the MOS level 1 file we are taking here, and starting from this quantity up till this, these are the various sort of model parameters, right, which needs to be inserted in order to evaluate the current versus voltage characteristics. For example, this source resistance, then you have got oxide thickness, then you have drain length, right. You have when you put a plus sign here in the starting of the comment, it basically mean it goes after this. Similarly, if you put a plus sign here, it goes after this. So, plus sign shows you the continuity of the statement with respect to the previous statement. Now, for example, if you look at a quantity known as xj, right, this is the maximum depletion width which can be handled at any point. Similarly, if you look at V max, is the maximum velocity of the charge carriers which are flowing through the device. Similarly, if you look at gamma, its body coefficient which comes into picture. So, there are many things which similarly, if you look at U0, U0 is basically the low field mobility, right, and it is always the order of centimeter square per volt second, right. Till this much you do have DC characteristics. VT0 is basically meaning its base level threshold voltage, right, which means that when you do not apply any bias, external bias, then the raw device will have a threshold voltage of approximately equals to 0.7 or 0.8 in this case. Then if you go to the subsequent parameter CGSO and CDGO, name gives you CGS, gate to source, then you have gate to drain, right, and then you have a junction capacitances here, right, and then and so on and so forth. So, you will have multiple junction capacitances here, right, and there will be many other parameters. The details of the parameters you can get in all the books, and you can have a look into what is the meaning of individual parameters, right, and these parameters are inbuilt within the SPICE model, and you generally do not change these parameters because these are empirically derived parameters which are available, device parameters, or you have written the device parameters. Let us look into the output part of it. Output part basically means what we are going to expect in the output side. So, we do ID versus VG here. If you look carefully here, this is ID versus VDS for a fixed VGS, we can do it here, and then we can have a family of IV curves. So, 3 types of output which we are referring to, and if you look, we are doing dot DC here, which is basically meaning I am doing a DC analysis. I discussed with you earlier also that there are three types of analysis: DC analysis, you will have AC analysis, and you also have a transient analysis. There are other analysis, but these are primarily the 3 analysis which are available to us. DC is when you apply a DC bias and you want to calculate the value of current at any one point of the node in the output characteristics, and that will be a DC current, right. That is known as a DC characteristics. AC is you do have a DC bias to bias it in the saturation region or linear region wherever you want it, but superimposed on that DC bias you also have an AC input. This AC input does what? This AC input tries to shift your Q point across the DC bias point, right, and as a result you will get an AC current, and this current can also be extracted or valued at any output point of the circuit. And finally, you have this transient analysis. Transient analysis are those analysis where you will have an input which varies like this and goes like this, or suppose. So, a sudden transient in the input voltage might happen, because of which you are supposed to find out the value of voltage or current in the output side. So, for all practical purposes, all the 3 probes here, all the 3 outputs here are dot DC. So, we will be doing a DC analysis, and we will be varying VGS from 0 to 5 volts at a step of 0.1 volt. So, this is 0 to 5 with a step of 0.1 volt. And then, so a dot probe basically gives you the command that at which output you will be getting. So, when you plot the graph, that this will be useful for doing that. Similarly, if you do IDVD, we have fixed VGS equals to 2 volts, and we vary VDS from 0 to 5 volts with a step of 0.1 volt, and we also store it at M1. Similarly, if you do a VGS, then what we do is that VDS is varying from 0 to 5 with a step of 0.1, and we do VGS 0 to 5 of step of 1, which means that we take VGS equals to 0 and then vary VDS from 0 to 5 with a step of 0.1 volt. Then you make VGS equals to 1 volt, and then again you vary VDS to VDS from 0 to 5 with a step of 0.1 volt. So, internally what SPICE does is that for every DC value which is being suggested by the user, runs the SPICE file internally and extracts the value of the current for that particular value of DC bias. Please keep in mind that all the device parameters which is stated at this particular point do not change with any other analysis. They are remaining constant, they are assumed to be constant, and that is one major sort of, if not but there are techniques by which you can change it, but prima facie the problem is that these are constants. However, when your device dimensions are very short or very small, then this becomes a function of these applied biases. Let me show you the IV characteristics here now. As you can see, on the y axis you have current, which is in microamperes. On the x axis you have voltage, and this voltage is basically VDS, and it is in volts, right. If you look, both x and y are linear axis. They are not logarithmic in nature, they are linear axis, right. They are linear axis. Now, as you can see, when you apply a 0 bias VD, this VD is 0 bias, then your current is also 0, which means there is no offset, right. When your input voltage is 0, your input currents are also 0, and this you can see from your level 1 model files also. The level 1 model files, if you check, and if you put VDS equals to 0 there, the everything within the parenthesis goes to 0, and therefore, independent of the value of mobility Cox or W by L, the output also goes to 0, and that is what you can see here. Now, this part is basically my linear part. In level 1 model, as you can see, it is almost like 2-piece approximation. Why 2-piece? Why? Because you have one piece here, especially for larger value of VGS. So, this is a VGS equals to 0, this is 1, this is 2, 3, 4 and 5. So, these are the various values of VGS which you see, and as you can see, two observations here. When your VGS is very high in level 1 model, it is almost like a 2-piece approximation, right. 2-piece approximation. What is the 2-piece approximation? It is almost like two linear lines collaborating with each other. I will show it to you. I will just show it here, so that it is easier for you to understand. You see, this line is one line, and this line is exactly another line, right. And what SPICE internally does is try to maintain continuity at the transition between the linear and the saturation. Whereas, if you go for a lower VGS value, so these are the points, this point, if I name them as say x, right, then if you plot a x curve, it will be something like this. It will be parabolic in nature, and these x curves are referred to as VD sat. All of you are aware of this point, and that should be greater than equals to VGS minus VTH. VDS should be greater than or equals to VDS at VD sat. Now, the idea therefore is that if you keep the device to the left of this green line, green parabolic line, it starts to behave like a resistor, and onto the right it starts to behave like a current source, right, and that is the whole idea of drawing this IV characteristics. But interestingly, for VGS equals to 0 and 1 volts, remember threshold voltage was approximately 0.8 volts, right. I will just show you to you from the previous file. This is the threshold voltage value, almost 0.8, right. When it is 0.8, actually, even when you apply a gate voltage of 1 volt, the overdrive is just 1 minus 0.8, and that is equals to 0.2. And in a saturation region, if you remember, it is mu n Cox W by L VGS minus VTH whole square. So, if you square this value, this comes out to be 0.04, right. This comes out to be 0.04. This is approximately equals to 1, and therefore, the current happens to be very small, right. It is almost close to cutoff. When you make your VGS equals to 2 volts, then you get a substantial amount of current, because 2 minus 0.8 is 1.2, and then if you square it, I get 1.44, and that adds value to the total current. However, one interesting observation of level 1 model itself is that as you move to the top, the slope of the curve at the saturation region increases. Here the slope is almost equals to 0, but here you have a substantial amount of slope available, right. So, this is the characteristics of a level 1 MOS file which is in front of you. Now, let me come to level 2 here. Everything else remains the same, apart from the fact that we are inserting this as level 2 here, and this is level 2 here, right. And we have added few extra terms in the device parameter part. In the device parameter part, some of the extra terms have been added, and these extra terms are which is different is lambda. which is the channel length modulation parameter, comes into picture. Then you have extra term which comes here, which apart from the previous part is another part is Kp, and so on and so forth. So, this model is relatively more accurate as compared to the previous case, but gives you a more higher computational time as compared to level 1. Again here we are doing IV, and then same thing, we are doing the IV here and we are doing IV here. This is ID versus VG. So, this is transfer, this is output characteristics, and this is family of characteristic. This is the family of characteristic. Everything else is exactly the same as level 1, no change is there. So, if you plot level 2 now, one thing which strikes you the most is the continuity of the lines. The lines are now more continuous, right. So, the IV characteristics are more continuous in nature. They are more continuous in nature, which means that the transition between the saturation and the linear region happens to be very continuous, and level 2 model is able to solve that problem of discontinuity. If you go back to this particular point, for example, you see you had a sort of, though they were continuous, but there was a sharp change, and that sharp change is not visible at this particular point. Second aspect is its VD sat has actually become larger now. So, VD sats are around, for this is, let us say 0, 1, 2, 3, 4, or maybe this is 1, maybe this is 1, 2, 3, 4, and then 5. So, for when VGS equals to 5 volts, right, 5 volts, then VGS minus VTH, let me see how much the VTH value is. The threshold voltage value is 0.8 here. So, I will get 5 minus 0.8 is 4.2, and therefore, you see this is somewhere cutting here, right, somewhere here. So, this is the edge of the saturation, this is the edge of the saturation, and beyond this you will have saturation, correct. So, this is slightly higher threshold voltage device, and that is the reason the whole curve has shifted to the right. Not only that, if you compare let us say 3 volts, no. So, let me see. So, you see when you take 3 volts here VGS, your current is actually 120 microamp, right. Now, if in this case when you take 3 volts, it is 200 microamp, and the reason is you do have higher mobility also has been considered for this case as compared to the previous one. This is a level 2 model, by the way, for your understanding. Let me come to level 3. Level 3 is exactly same as level 2. There is not much change here, except that we insert certain extra term here like TPG and other terms here, but it's level 3 which we are referring to here, and this is level equals to 3 here. And we try to find out IDVG, IDVD, and families of IDVD. And let us look at the IDVD curve here. You see now interestingly the curve have not only become more and more continuous, but even with lambda, I think lambda is already there inside this value, that though lambda has not been taken here in this expression, but lambdas are inbuilt. So, when you do not take a lambda, you see what happens is your output characteristics are more flat at the saturation region. So, this is for I think 0, 1, 2, 3, 4, or maybe this is 1, 2, 3, 4 and 5, right. So, this is how it moves top. Below this is cutoff, this is saturation, this is linear, and you will also have a non-linear part here. So, you have a linear non-linear saturation part which is already inbuilt within this network. So, this gives you a framework of finding IDVD and IDVG transfer characteristics. This is again a transfer characteristics here. Slightly we have made changes in the netlist, and this netlist has been generated internally, and therefore, we are giving VG from 0 to 1.8 with a step of 0.5, and we got IDVG curve something like this. And if you look its schematic entry, then you see this is my NMOS, the device which we are giving, this is my DC VGS and this is my DC VDS, and I am varying my VDS from 0 to 1.5 with a step of 0.5 volts, right. And as you vary it, I try to measure the current and it sees here. So, the length of this device is 180 and the width is 400 here, and if you therefore extrapolate it backwards in a sense, you will get the threshold voltage somewhere between 0.4 and 0.6 in this case. Now, you see this is the library file which we include, right. So, this is an expression from LTspice, right. This is a example for LTspice. From LTspice you have a standard model file, you extract that model file, and when you say .lib is the library file from where you are extracting, you include the .lib file from 180 nanometer TSMC. TSMC is the one which is providing you with these model files, and therefore, you write down here TSMC 180.lib when you say that library file is extracted and brought onto the schematic, and you get the plot IDVD from where you can extract threshold voltage and many other things. Similarly, NMOS output characteristics you can draw here in LTspice. So, this is by default a higher level of spice automatically taken into consideration. So, this is now IDVD, right, IDVD for a fixed value of VGS, and we got the same characteristics as expected from our previous discussion in the case of output characteristics. On the right hand side, if you see, you have this M1 which is the MOS transistor, and you are trying to measure the V out at the drain of M1, and you are applying the gate voltage at the gate side of M1, and your source is grounded, and you are applying a VDS on the drain side, right. So, this schematic onto the right hand side sort of gives you the way how a circuit will be designed using this quantity, right. And so, this is gives you an output characteristics of NMOS. This shows to you the DC characteristics of a CMOS inverter. If you look carefully, there are two devices, because now you will have an NMOS pull down device and PMOS pull up device, which you already know when we were doing it. So, it is something like this which you will follow. So, this is my PMOS and this is my NMOS. You apply a VG here and you try to take the voltage at the output here. This is V out and this is your C which you see. When you apply 0, this switches on and output swings to VDD, and when you apply 1 here and swings to VDD means 1, and when you apply 1 here, this is on now. When this is on, all this is get discharged and the voltage goes to 0. The same thing appears on the plot here. So, we are plotting V, this is my output voltage versus input voltage. My input voltage is low, my output is high, and my input is high, the output is low. The red colored is the output, and the V in is given in this manner. The input voltage is a constantly rising input voltage in this case, right. So, for low values of input, output is high, for high values of input, the output is low, right, and this gives you the output data for a 180 nanometer design. This is the W by L ratios for both PMOS and NMOS. So, we have not ensured that the TPHL means high to low transitions and low to high transitions are exactly the same, and we also say that it is 0 to 1.8 volts are available to us. So, this is a brief idea of the DC analysis of a CMOS inverter. Now, let us look at a transient simulation here, and everything else remains the same. Only statement which you see is this statement .trn. So, .trn is that the output file should be a transient file. You do a transient analysis on the network, and what you do, you give up input voltage. The green colored is the input voltage and the red colored is the output voltage. So, when the input voltage goes low, right, the output voltage goes high, and that is what the inverter is doing. And you can see here that the parameters are defined as 0, 200 nanosecond, 5 nanoseconds and 200 nanoseconds. These are the rise time and fall time for the input pulse which you are giving, right, and then what is the maximum pulse width which you can handle in this case. So, all these data are shown here, and again you call the library file from a standard MOS structure of 180 nanometer, and then this is how you give the input pulse, right. It is between 0 to 1.8 volts. We give various values of the delay pulse here, right, and we say that this is the rise time, fall time for the input pulse. And when we do a transition, we say that we will do a transition for 5 nanosecond. Within the 5 nanosecond, we try to calculate it, and that gives you the output result shown here, right, which gives you the value of the output characteristics. This is a final example of a 3-stage ring oscillator. 3-stage ring oscillator is shown in front of you here. So, I have 3 inverters connected in series like this, and the output of the last one is fed back into the input side. And interestingly, the V out shows me, if not a very good ring oscillator, but nonetheless gives me an oscillatory tendency from 1.8 in the positive direction to 0 volt. So, the peak to peak swing of the ring oscillator is 1.8 volts, and that is expected also because you are giving a VDD of 1.8 volts and the minimum value is 0 volts. So, you are grounding it properly. This is the device parameters which you are feeding, right. For each of the transistors you are giving the device parameter, you are including a 180 nanometer, you are doing a transient analysis and you are trying to find out the value of the output voltage. Now, from this we can find out what is the delay sort of in the ring oscillator between each point. However, the one point you should see is that we are doing all in 180 nanometer. As a designer, you can be also told to work at much lower technology nodes. So, I would recommend that first handle this one and then go for a lower technology nodes, and let us see if you can actually do a 3-stage ring oscillator design. Now, we are trying to find out the frequency response of a single stage amplifier. So, single stage amplifier is basically, this one is a single stage amplifier. This is the voltage divider network which is there, 200 and 100 kilo ohms. So, the voltage across 100 kilo ohms is appearing between the gate and the source of the device to switch it on, right. We have a blocking capacitor here which is C2, and we also have this resistance R1 1000 ohms across which we are trying to extract the output voltage, and it is run by a voltage source of VDD, channel length 1 micron, width 250 micron, and these are the values of your gate to source and gate source to drain capacitances. And we are inserting a sine wave, right, whose peak to peak is 0.9 and 1 mega is the frequency of the sine wave. So, with this, let me show you how the graph looks like. So, I will not talk about phase too much, but I will look at the gain. So, as we all know from our theoretical analysis, the gain actually first increases and then drops down because of certain reasons. We are not going into details on that, but this gives me a very good input output profile. So, this is the gain in dB. Gain in dB is 20 log output voltage by input voltage, right. Input voltage peak to peak is already set by the user. Just SPICE has to divide the output voltage with input voltage and put a log sign multiplied by 20, you get the value here. We define the bandwidth as the 3 dB bandwidth. So, my highest is 20 dB, I will go around 17 dB and then try to check out what is the bandwidth here. So, I can calculate the bandwidth from this one. I can also calculate what is the gain available with one, right, in this case. We can also plot the phase very well. So, both phase plot and gain plot can be done on a SPICE model file. So, with this, let me recapitulate what we did for this lecture and the series of this lecture. We looked into the first of all level 1, level 2 and level 3 models, and we then tried to find out the IV characteristics of the device, current versus voltage, and then we looked into the transfer characteristics of the device. Right. So, we looked into IV and we looked into the transfer characteristics of the device. Then this was all on LTspice, right. Then on PSpice we looked into the NMOS transistor, and this was all on PSpice, and then we went into characteristics of a CMOS inverter, right, and these are all long channel by the way, and finally we went for the ring oscillator, and then last was basically the single stage amplifier, CMOS amplifier. So, I gave you some of the examples of both analog mixed signal as well as basic devices, and tried to show to you that PSpice can be quite helpful for your initial understanding of the subject and as an add-on to the subject being taught to you in your universities. So, with this, let me stop today for this lecture, and thank you for your patient hearing.